Elite hackers can be lethal on the network even with minimum tools available. They can craft their own packet sniffers as they possess impressive knowledge about networking and low-level programming. In this video, you will learn how network sniffers are built, see how packets look like under the hood, and understand how binary data is transported across the wire. Let's fire up Terminator. And initialize a Git repository. Let's name our script sniffer.py. During start, I normally create the base structure of my script. That is for me to have a high-level overview on what I want to do. In this case, we want to import first all necessary modules that we will be using. Since we will be dealing with a lot of IP networking related stuff, it's good to import IP address module. Then same with socket module, we will need this to handle low-level data buffers. Let's also import struct, as this will help us in converting printable characters into byte objects and vice versa. Sys for handling program exit codes. And finally argparse to make our script customizable. Next is we want to create the first option that we will use for our script. First, let's build our parser object and add some useful description. Let's put network packet sniffer. Since this is a traffic sniffer, it makes sense to add a parameter for the IP address to sniff on. Let's use --IP as the option. Let's also add help message and make this as a required parameter. That parameter is not yet accessible to us. So let's don't forget to call the parseArgs method to extract that from the internal namespace. Now that our parameters are set, we need to define some class and functions that will drive the script. Since we are handling network packets, a packet class will be best suited for this. For now, let's use passStatement as a placeholder. We need something that will call our class, so let's add a sniff function and add a placeholder as well. Finally, let's add the classic if name equals main conditional block so that we have both ability to run this as a standalone program or import this as a module. With this base structure, it is easier to understand the flow of the program. We can also see clearly what the script is intended to do. Let's save and commit this in Git. Since we now have the base structure, let's put in the different pieces of the puzzle. First, we need to be able to extract the necessary information from the IP header. Let's put it under the init method of our packet class. In this method, we want to pass a bytes object that holds the buffer containing the packet. Then we will extract the IP header from the bytes object. But before that, we need to understand how an IP header looks like under the hood. When a data crosses the network, it undergoes a series of transformation when passing through different layers. That transformation is called encapsulation and decapsulation. This process adds or removes headers that are needed on lower level of the OSI layer. In this video, we will focus on the IP header, which contains information needed for network layer. An IP header consists of multiple fields with varying sizes. The typical IP header length is 160 bits or 20 bytes. The first 4 bits tell you the version. In IPv4, this is set to decimal value of 4. The next 4 bits is the header length, which is typically set to decimal 5. It's decimal 5 because it is the total size of header in 32-bit increments. The next 8 bits is the quality of service, which adjusts the priority of packets compared to authors. The next 16 bits is the IP header length plus the data length. Packets can be fragmented or divided into several bytes if they don't fit on the network interface. If fragmentation happens, we need some sort of identifier which will tell us on which packet the fragment belongs to. That is the purpose of this next 16-bit field. Still related to previous field, this next one indicates whether the packet needs to be fragmented or not. This is a 3-bit field that stores the fragmentation flags. The last 13-bit field is the fragment offset, which indicates the position of the fragment. If you also notice, this 32-bit field indicates information about packet fragmentation. This is crucial, as we don't want the packets arriving out of order or some parts of it missing. The next 8-bit field is for time to live, which is similar on what you see when pinging a computer. Time to live prevents the packet from traveling across the network endlessly. The protocol field is also 8-bit wide. Each protocol has its own value, but the most common is 6 for TCP, 17 for UDP, and 1 for ICMP. The last 16-bit field is used for checksum to ensure the IP header is not malformed. The next one takes the full 32-bit space and used to store the source IP address. This 32 bits are divided into 4 8-bit parts, which are called octets. Similar with the source IP, the next 32-bit field is used for destination IP address. The last 32-bit field is for optional bits, which is not often used. For simplicity of this video, we will discard it from our data buffer. So in summary, the IP header consists of vital information needed to forward a packet from one point to another in the network. With this knowledge, let's now go back to our script and extract these different fields. Okay, so what is this code? The data buffer we will be expecting from the socket will be a sequence of bytes objects. We need to convert it into something that will allow us to reference the individual fields easily. In this case, we can use the Python struct library to unpack it into a tuple which consists of fields as the items. We are getting only the first 20 bytes of the packet since we only want the IP header part. That means we will disregard anything after that, which is the actual data. In order to unpack the first 20 bytes properly, we need to tell struct on how the individual fields will look like inside the tuple. This is done via these format specifiers. We will arrange them in Little Endian format since we are using x86 CPU architecture. The first byte consists of the version and header length, so we will unpack them inside a 1-byte integer. Both version and header length are 4 bits long each, but struct is only capable of unpacking 1 byte size and above, so we need to do some bit manipulation later. The type of service field is also 1 byte, so we will use same format. Packet length field is 16 bits, so we will unpack it into a 2-byte integer using H. We will use same format for fragment identifier and offset. If you recall, there is a 3-bit flag field between fragment identifier and offset. But for simplicity, we will just include it inside the 2-byte integer. Time to live and protocol number are 8 bits wide each, so we will unpack them into a 1-byte integer. Header checksum is 16 bits large, so we will unpack it into a 2-byte integer. Lastly, both source and destination IP addresses are 32-bit wide, so we will unpack it into a 4 bytes character. Let's go back to the script and extract the first 2 fields. As mentioned earlier, we need to do bit manipulation to extract the version and header length properly since both of them are 4 bits. Let me explain this next 2 lines. A byte consists of 8 bits. Each 4 bits is called a nibble. In the first 8 bits of the IP header, the first nibble is the version while the second one is the header length. In order to get the version, we need to right shift the bits by 4 places. We can do that by prepending 4 zeros, causing the last 4 bits to fall off, making the higher order nibble go to the right by 4 places. To do that in Python, we need to use this technique with 2 greater than sign, followed by the number of bits you want to shift. We will follow similar technique to get the lower order nibble. Only difference is that this time, we will apply Boolean AND operator against 0xf. In binary, 0xf consists of high order nibble being zeros while the lower order nibble being ones. Performing this operation will convert the higher order nibble to zeros, while making the lower order nibble still intact and have same value as before. We can do this technique in Python using ampersand operator followed by the special byte 0xf. Now that we handled some of the tricky parts of the IP header, let's proceed with the next fields. Most of them doesn't need special handling, meaning we can just access them via their indices. The next field is the type of service, which is the next item in the tuple, so we will access it via index 1. We will do the same for the header length, which is item 3. Next will be the fragment ID on item 4. Fragment offset on item 5. 6th item will be the time to live. Item 7 will be the protocol. Next is the header checksum. Then the last 2 items will be the source and destination IP addresses. Although we unpack both source and destination IP addresses into 4-byte characters, they are still not in dotted decimal notation. In order to fix that, we will use the IP address library. We will do the same for the destination IP address. To start with basic functionality, let's try to capture first ICMP packets. Then once we confirm this is working, we will add TCP and UDP packets. The 7th item of the tuple is an integer that identifies the protocol type. In order to better understand the output, we will create a dictionary of mappings between the integer and the protocol name. Since ICMP is 1, we will use it as the dictionary key. Our Sniffer script is simple, and we only want basic protocols. So let's add a code that will throw an exception if the packet captured is not using the protocol we defined in the map. Here we are using Python try block, and we will store the exception in a variable. We now then send that exception into this F string so we can see what are these unwanted protocols we are seeing on our capture. Let's don't forget to fix the typo on the operator sign. Now that our packet class is constructed, next thing we need to do is to create the sniff function that will use that class. We already created a placeholder for the sniff function, so let's go straight to it. Let's set the protocol that we will use. For now, we care only about ICMP, so let's use the IP proto ICMP object from socket library. Then we need to initialize our sniffer socket. The address family will be AFINet. Socket type will be sock raw, since we want to capture raw packets and do the processing within our script. Then last parameter will be the protocol type we just set above. We will bind this to the IP we will use. Let's leave the port 0, as we don't want this to listen on any port. Finally, we need to set additional socket options to make sure the IP headers are included. Let's don't forget to pass the listen IP address to sniff function. And update the function call inside main to use the IP address we will specify as a command line argument. We just initialize the type of socket we are going to use to sniff packets from the network. If you are familiar with basic socket programming, you will notice this is similar on how to create a socket server listening on a particular port. Difference is that this time we are not listening on a port, and the socket type we are using is sock raw. This is not yet complete, as we still don't have the code that will receive the actual packet buffer from the network. So let's do that. We will run the sniffer endlessly until the user hit Control-C. Then we will capture all packets and store it in a huge buffer size so we can catch more data on each loop iteration. Once our buffer is full, we will pass it to an instance of our packet class we created on the earlier section. One processing we want is to print some of the important information on the IP header, such as the source and destination addresses. We still haven't created a method for this, but let's add a placeholder and name it as printHeaderShort method. To close the try block, we will exit the script once it catches a keyboard interrupt exception. Now let's go a few lines above and create the printHeaderShort method. This is just a simple method containing an F string that displays the protocol type, source, and destination IP addresses. Now that we were able to sniff ICMP packets successfully, let's start with the main juice of the script, which is capturing TCP packets. First, let's add an argument to specify the protocol type we want to sniff. We will use --proto as the argument. Let's add a useful help message and make this as a required parameter. Then let's update our protocol map by adding the TCP key and value. TCP is represented as integer 6. Since the protocol to sniff will now vary, we need to make sure the socket protocol we will use adjusts automatically. So let's add a condition here that uses the correct socket protocol type depending on what is supplied as a command line argument. Now let's do a quick test. Let's open up a web server inside our local Kali machine. Then let's fire up the sniffer script, but this time let's specify TCP as the protocol to sniff. Next is we need to access the web server to generate a traffic. We can clearly see that it is working now, as it is successfully capturing the TCP packet from our web requests. But this is not too interesting, as it only prints the protocol and the IP addresses. In order for this to be a fully functional sniffer, we need to be able to see the actual data inside the packet. So let's modify our script to do that for us. Let's add an argument that will allow us to print the data. This will hold a Boolean value and make this optional. We want to make it optional to limit the noise in scenarios where you only want to see the source and destination IP addresses. Then we will create a method to print the data. We know that the IP header is the first 20 bytes of the packet. That means anything beyond that is the actual data, so we'll slice the byte sequence the opposite way. When data starts to flow, it will be hard for us to see the start and end of it, so let's add some useful identifiers. We only want the ASCII printable data since those are the only things we can understand. Others will be just garbage and won't be really useful to us. In order to get the ASCII representation, we need to have a basic understanding on how characters are encoded and decoded. Character encoding is the process of assigning binary representations to characters so they can be transmitted over the network, stored on disk, and display on screen. ASCII is an encoding scheme that can represent up to 128 characters. We want to display only ASCII characters, so we will add a condition here to filter bytes whose decimal value is less than 128. Then, in order to display the character representation, we will use Python char function and run it against the decimal value. Let's also remove the trailing new line to make the output clear and easy to understand. If it encounters a non-ASCII character, we will print a dot sign. This is the same thing you see on other packet capture tools such as TCP dump or Wireshark. Let's also remove the trailing new line. Lastly, let's don't forget to call this method when the -- data argument is supplied on the script. I think I saw a typo on the print statement, so let's fix it first before testing the script. Let's fire up the sniffer. Let's rerun the script with -- data and generate again a web traffic. The TCP sniffer is working as we can see the HTTP response from the web server. Let's see other possible traffic we can sniff. The basic functionalities are working already, but there is nothing stopping us from adding other features. For example, sniffing through busy network will produce a lot of noise, so we may want to exclude or filter specific IP addresses only. Or we may add more protocol, aside from TCP and ICMP. Thank you for joining me in this video. The final version of this script, which includes extra features, will be published in GitHub, so stay tuned on my upcoming community post.